Okay, we are going to be talking about the law of sines and the law of cosines. And if you remember when we were working with right triangles at the beginning of the semester, we talked about solving a right triangle, and that was like given an angle and a side. We found all the other angles and the other sides in the triangle. And so now what we're going to be doing is talking about solving oblique triangles. So an oblique triangle is a triangle that is not a right triangle. And if we're given either two angles and a side, or two sides and an angle, or three sides, we're going to be able to solve an oblique triangle. And there's several cases here. And for three of these cases, we're going to use the law of sines, and for two of them, we're going to use the law of cosines. Okay, so basically, if we're given an angle, and a side, we can use the law of cosines to find the other angles and side. And this is an example, two angles and then a side that's not between those two angles. Okay, if we're given an angle, a side, and an angle, so here we're given two angles, and then this is the side connecting those. We can also use the law of sines to find the other sides and angles. And if we're given a side, and an angle, so here we're given a side, and an angle, but the angle is not between the two sides, okay? It's the side, and then the angle. We're going to be able to solve this as well. But this last case here, this is the ambiguous case. And we will look a little bit about this, but I don't want to spend too long on this. But I do want to make you aware of that. These two will not be ambiguous, but if you're given two sides and an angle, then you can use the law of sines, but it's known as the ambiguous case. So now, if you're given a side, an angle, and a side, so now the angle here is in between the two sides, so the two sides make up the angle. You're going to be able to use the law of cosines to solve the triangle. And if you're given a side, and a side, so you're given all three sides, again, you can use the law of cosines and solve the triangle. So the only thing that's really not included here is if I'm given three angles, like if I was given all three of these angles. So I don't know, let's say this was 75 degrees, and this was 30 degrees, and this was 40. Let's see, I got to make sure they add up to, this is 105, so this is another 75, I think. This would be another 75 degrees, which doesn't make sense. Let me do 65 and 85 or something like that. So if I'm given three angles, you can't solve this. You can't find the sides, because I could make another triangle with those same three angles. So we would have 65 degrees, 85 degrees, and 30 degrees, and it's just a smaller triangle. So any triangle that has those three angles will be similar to these triangles here. It'll just be a different size. It'll have the same shape but a different size. And so the three angles don't determine a triangle. You have to have at least one side in order to determine the triangle. Okay, so basically if we're given three pieces of information, we're going to be able to solve any triangle, even if it's an oblique triangle, except with the exception of it given the three angles. Okay, we need at least one side. And so the first thing we're going to do is we're going to learn how to use the law of sines to solve the triangle. Okay, and so the law of sines, basically, we'll say like this is angle A, and then across from angle A, we'll say that's side A, and then we'll say this is angle B, and across from angle B is side B, and this is angle C, and across from angle C is side C. And basically the law of sines, what it says here is that the sine of the angle divided by the side, so the sine of A divided by the side A is equal to the sine of B divided by the side B, is equal to the sine of C divided by the side C. Okay, and all three of these ratios are equal. This actually makes sense because, you know, the wider the angle, right, the bigger the side. So this ratio, if you got a bigger angle, this would be bigger. And basically the ratio of all three of these are related in that way. So it actually makes sense. And you can actually flip these, and you could write it this way as well if you wanted to. And sometimes it just makes the algebra a little bit easier to choose one form or the other. Okay? But that's basically what the law of sines says. It actually ends up being pretty easy to prove this. And I think it's worth showing the proof here. So let's actually do that. So this is angle C inside C, angle A inside A, angle B inside B. Okay? And what I'm going to do is I'm going to drop this down like this, and we'll let this be like the height. And then what you can see here, this is like a right triangle here. And so I can say that the sine of A is the opposite over the hypotenuse. So it would be the H over the B, right? And then the sine of B is the opposite over the hypotenuse. So this would be H over A, just like that. And so then you could rewrite this. H is equal to B sine of A, or H is equal to A sine of B. Since both of these are equal to H, what you have is B sine of A is equal to A sine of B. And then I could divide both sides by B and both sides by A, and I would get sine of A as sine of B. I should write it like that, as sine of B is to B. And that would be this part of the ratio, right? So I could do a similar thing if I reoriented the triangle, drop down a different diagonal, and I could show sine A over A is equal to sine C over C, and then that would show that all three of them are equal. Okay, so it's really a pretty easy proof to show. It's not that complicated here. Okay, so let's actually use it to solve some triangles here. Let's see how it can be used. And these are actually the ones that I had at the very beginning here. This is the one for AAS and ASA. And these are the two cases that are not ambiguous. Okay, so I'm going to solve these, and then I'm going to make a whole other video to show you what's going on in that ambiguous case. So here's the idea, is with the AAS, you see that I have the an angle and the opposite side. So when I'm using this, I'm not even thinking about A and B or whatever, but what I'm, this here, let's say, is X. So what I'm thinking in my mind is the sine of this is to 3 as the sine of this is to X, and that like sets up a proportion. And you can flip it either way. So to make your algebra easier, what I can do is I can say this X is to the sine of 55 degrees, as this 3 is to the sine of 40 degrees. Okay, that's a proportion. And so now the algebra is real easy. I just multiply both sides by the sine of 55, and I get 3 sine of 40 degrees times the sine of 55 degrees. And this is going to give me my X. Okay, so 3 divided by the sine of 40 degrees times the sine of 55 degrees. And I get like 3.8 here. We'll round to the tenths place. And so what that means is that this side is 3.8. Okay? Now I can continue on and solve the triangle. What I need is this angle, and then I could call this y if I wanted to. Now how can I get that angle? Well, they all add up to 180 degrees, right? So 180 minus 40 minus 55. And I get like that this angle is 85 degrees. Okay, so now I can do something similar. I can do y is to the sine of 85 degrees. So y is to the sine of this, as 3 is to the sine of 40 degrees. And so y is equal to 3 sine of 40 times sine of 85 degrees. So 3 divided by sine of 40 times sine of 85 degrees. And that's like 4.6. So this is 3, this is 3.8, that's 4.6. Now we've solved that triangle. We got all the sides and all the angles. Okay, so let's do one more here. This is ASA, so now the two angles are on either side of this side. And so what I'm going to do is I need at least, if I want to solve and find these sides, I need at least one pair where I have the angle and the side. And I can get that here by finding this angle. So I'm going to do 180 minus 35 minus 20, and I get 125. So this is 125 degrees. So now I got that one pair. So now I could call this x and this y if I wanted to. And so basically I have x is to the sine of 20 degrees as 100, or 10 inches is to 125, sine of 125 degrees. Okay, so let's see here. This would be 10 sine of 125 degrees times sine of 20 degrees. So 10 divided by sine of 125 times sine of 20. And I get that this is approximately 4.2. Okay, so that would be this side here, 4.2. And now this last one. And let me say, I didn't emphasize this before, but when you set this up, if you have the length of a side on top, and then the sine of an angle on bottom, you just got to make sure that the other side matches that. So y is to 35 as, it'll be 10 is to the sine of 125. Okay, so in this case, the side lengths are on top, angles are on, sine of the angles are on bottom. The side length divided by the sine of the angle. Okay, they have to match like that. Okay, so that would be like that. So now I got 10 divided by sine of 125, and then multiply that by sine of 35. And this is approximately 7.0. And so that would be this side. This would be 4.2. That would be 7.0. Okay? So that's the idea behind law of sines. You can use it to find these missing sides. That's what we've done so far. Now what we haven't done is we haven't used the law of sines to find a missing angle. And so if you're given two sides and an angle, then you can do that, but as it turns out that there's several possibilities. They call it the ambiguous case, because you can either get two solutions, two possible triangles out of it, or just one solution, or possibly no solution at all. And so we're going to look at the ambiguous case in the next video.